Jnanam Paramam Dheyam. Knowledge is supreme.
The fourth problem is that the particle is subjected to magnetic field along the z direction and it has some energy with the Hamiltonian operator given to you as E by mc into B sz, where B is the magnetic field and it is along the z direction, and we will rewrite this in terms of omega first. So, omega is E B upon 2 m c. So, here I will write omega s z, okay, where omega is E B upon m c. Hamiltonian operator in terms of omega, and S z is the Pauli spin operator along the z component. You can write this S z as in terms of Pauli spin operator in the z direction. So, S z is h cross by 2 sigma, this is also we all know. Now, we will start by writing or assuming that ket 0 and ket 1 are the eigen ket or the eigen basis of Sz, are eigen basis of Sz. And recollect in the lecture 0 was denoted as plus and 1 was denoted as minus, I think. So, here 0 indicate 1 0 state or 0 1 state and 1 indicate 1 0 state. Okay. So, we denote instead of plus and minus ket, I am denoting it as 0 and 1, please do not get confused. So, the unitary time evolution operator is, I will write it as u t comma t naught. So, the evolution of time is from t is equal to t naught to some time t is written as e raised to minus I h operator, Hamiltonian operator t minus t naught upon h cross. And we know what is the form of Hamiltonian operator, it is of the form omega s z. So, e raised to minus I s z times omega upon h cross into the factor t minus t naught, which is here. So, this will be in the Dirac notation, we can write S z or this exponent as omega t minus t naught upon h cross ket 0 0, okay, plus e raised to I omega t minus t naught upon h cross ket 1 1. Remember, the ket 0 and 1 are the eigenbases of Sz with eigenvalues 0 and 1. Eigenvalues, these are eigen ket. So, here we will have e raised to minus I omega t minus t naught ket 1 and another ket in terms of Sz basis. This exponent you can rewrite with eigenvalues 1 and minus 1, I am sorry, 1 and minus 1, I made a mistake. Here the exponent e raised to I theta, you can write it as cos theta plus I sin theta. So, I write first term as cos omega t minus t naught upon h cross, okay, and the ket from the first term of this, and the first term of this will give me, because again I will have cos theta, that is cos omega t minus t naught upon h cross, okay, plus e raised to minus I theta will give me minus I sin omega t minus t naught, correct, upon h cross times 0 0 minus 1 1, okay. First term will give me minus I sin theta times this plus I sin theta, this will be minus, okay. Then what we do next is u of t naught will be, we can rewrite as cos omega t minus t naught upon h cross, okay, times the unitary operator or the identity operator minus I sin omega t minus t naught upon h cross. This is what we obtain in terms of times this term. This would denote the identity operator, top one. However, this would denote Sz. In the Sz basis, I will have 1 and minus 1. Sz you know is 1 0 0 minus 1, okay. So, in terms of eigenbasis of Sz, you obtain Sz, right. Now, here just a note that if you consider omega is E b upon 2 m c h cross, then you will obtain, so this will become actually t minus t naught cos omega t minus t naught upon 2, okay, or rather you have to multiply by 2 because I have a 2 in the denominator times the identity operator minus I sin omega t minus t naught divided by 2. So, if we start writing omega as 2 e by e b upon m c h cross, then we obtain this result. However, we had started this by writing omega as e b upon m c. So, you obtain this result. So, it is just the way you define omega, okay. We will get the same result. Okay, here I have to write sigma z. Here also I have a sigma z or sz term. So, this was sz, here this was sz, okay. So, in terms this is sigma z, okay, and this we have included in our expression over here sz, okay. Right. So, the unitary operator can be expressed in terms of cos of the identity cos theta. I can call this entire term as theta. So, cos theta times the identity operator minus I sigma sz sin theta, right. Let us go to the fifth problem. Okay, fifth problem is based on the fifth problem is based on the orbital angular momentum operator Lx and Lz. Now, we have already seen since first tutorial we are trying to calculate the eigen values and eigen function, the wave functions. So, you can do this computation by yourself, but let me give you some hints. What are the first part is what are the measurements, what are the possible results of measurement of Lz which is asked to you, and you have to find the normalized eigenstate of Lx in terms of Lz basis. And third part is if the particle is in Lz state and Lx is measured in that state, what are the possible outcomes that we get. So, Lx is given to you and Lz operator is given to you. From Lx and Lz you can see that Lz has eigen values 1, 0, minus 1. These are the 3 eigen values, and the corresponding eigenkit or the operator the vectors would be, I denote it as plus, 0 and minus. Okay. So, here plus is 1 0 0, this is the standard basis, and minus is this. So, the eigenstate of Lz are 1 0 minus 1 and eigenvalues are 1 0 minus 1 and eigenstate are plus 0 and minus. Now, from this you can try and calculate what is the eigenvalues of Lx. Eigenvalues of Lx are also 1 0 minus 1. It is easy to check. Okay. It is easy to check this, and we have to now write, let me call this is the eigenvalue and the eigenvectors or the eigenkits values okay, so that there is no confusion. So, eigenkets, let me denote them by plus ket with a subscript x, 0 with a subscript x and minus. Now, you have to find out the eigenket of, that is plus x in terms of plus 0 and minus, that is in the SZ basis. So, once you do that, you will be able to calculate the eigen vectors or the possible measurements of LZ. We have seen that these are the possible measurements, that is it can take eigen values 1, 0, minus 1 and the corresponding eigenkets we have seen. For LZ we have to find out, so that we can write the normalized eigenket LZ in Lx in LZ basis. I can give you a hint that if you want to calculate ket plus of in the x basis in terms of ket plus 0 and minus, these are the eigen basis of LZ. So, in terms of LZ, if you want to calculate, let us write a linear combination of these such that L plus, so Lx has the eigenket plus x in terms of the linear combination of the eigenbasis of LZ. Now, how will I obtain this coefficients A, B and C? Simply what you can do is use energy eigenvalue equation. Right, that is Hi. So, you have Lx plus is equal to eigenvalue is say lambda 1 x plus x, and you will use normalization condition. And you know that plus 0 and minus kets are orthogonal. So, normalization condition is a square plus b square plus c square is equal to 1, and first part you can just substitute for Lx, substitute the value of lambda 1 which is the eigen value, say if you start with 1 as the eigen value, and just write plus x as A, B and C and see what you get. So, what I have obtained is plus ket in x basis will be 1 by 2, I have plus root 2 ket 0 plus ket minus ket gives half 1 plus half ket 1 ket plus minus square root of 2 ket 0 plus ket minus, and the third one is 1 by root 2 ket plus minus ket minus. So, use hint to get this result. You will do it for plus, minus as well as ket 0 and obtain the corresponding coefficients A, B and C, and then you write the result. So, it was very simple. This was part B of this problem, last problem, and in the last part, if the particle is in Lz state, which is Lz is one state and Lx is measured in that state, what are the probabilities? So, again you should know what are these kets, plus, minus and 0 in x basis, and you have to calculate the ket, these kets on plus. That is, what I am trying to say here is the possible outcomes for the measurement are 1, 0, minus 1, okay, with the probabilities what will the probability? So, for plus x on, so Lz is in state 1, which will correspond to eigenket plus. So, we have to find out the probability of measurement on state Lz is equal to 1. This will give me 1 by 4. You can just do it. Okay. We have obtained already the eigenket plus, minus and 0 from in Lz as well as Lx basis. Using that information, you can calculate the result. So, for plus you have 1 by 4, for minus the probability is again 1 by 4, and for ket 0 on 1 Lz is equal to 1 is simply half. Okay. So, from the coefficient itself you can infer this result. So, let us stop here with these exercises. You can also have more exercises on orbital angular momentum operator, on commutation of these operator Lx, Ly, Lz, on spherical harmonics like y plus y, combination of L and ML, and those problems you can try it yourself.